Hello everyone, my name is Tien and Nguyen. I am research engineer at CTICM, Centre Technique Industriel de la Construction Métallique, based in France. Today is my first participation to Eurosteel, and I would like to present to you our research result on macro modeling of 3D tubular column-to-truss beam joints. After some introductions, I present proposed analytical solutions and a model of springs of the new steel joint. They will be illustrated via a numerical example, and I will finish my presentation by giving some conclusions. As you know, modular construction systems have many advantages. They reduce the construction time, construction cost by ensuring the excellent quality of the final product. Many ideas of innovative modular construction systems have been proposed. One of them is started in the framework of the European Research Project, Innovative 3D Joints for Robust and Economic Hybrid Tubular Construction, called 3D Joints. It consists of a truss beam made of conformous section connected to tubular columns of square hollow section or rectangular hollow section by using innovative steel joints. This innovative steel joint consists of two main elements, orange part and blue part as indicated in the picture. The orange part, called T part, is uh, both thrust of the truss beam, while the blue part, called socket, is routed to the column face. And finally, bolts are implemented between the two elements of the joint to ensure the ultimate strength of the system. However, no calculation methods are available for this type of joint. As the time being, the current component method given in Article 3, Part 1H covers only steel joints with beam and column of I sections. So one of the main tasks of the project is to extend the component method to new steel joints. In this presentation, we deal with only one component of this joint. It's a column face subject to tension or compression as a location of the socket. In order to characterize this component of joint, we have to solve some elementary problems. Problem 1, we consider a supply supported rectangular plate subject to one locally distributed load that is transmitted from one part of the socket. In the second problem, a rectangular supply supported plate subject to two locally symmetrical distributed loads are transmitted from both parts of the socket. In the third problem, we take into account the influence of adjacent column faces by considering a supply supported rectangular plate subject to distributed moments along its edges. And finally, one solution of these three problems will be applied to the tubular columns subject to two symmetrical point loss at each face. In the first problem, the plate is divided into three parts by these two lines PR and ST. For each part of the plate, the displacement at any point may be expressed as a summation of infinity hyperbolic functions as given in the screen. Constants of this function are determined by using boundary condition as at of the plate, displacement and bending moment are equal to 0, and continuity condition along these two lines PR and ST. For example, the parameter AM is a function of the integer number M, the dimension of the plate A and B, the TS thickness of the socket, HS the length of the socket, and C location of the socket. In the second, we consider both parts of the socket. The solution to this problem is easily obtained by superposing two solutions of the previous problem with two different locations of the socket, plus and minus C. So in one face of the column is simply supported only at its long edges. By assuming that the column is long enough, the above solution can still be applied because that the two other free edges, the displacement and bending moment are some equal to 0. So the solution depends strongly on the number of terms in the summation and the length of the plate. Two questions have to be answered. How many terms are to be taken into account? And what is the effective length of here in this figure? We plot the plate displacement as center in function of the number of terms, m. The convergence of solution may be observed for m greater or equal to 9. In the below figure, we plot the deflection of the plate with different values of the plate length. A good agreement is obtained when the plate length is at least 5 times of the plate width. In the third problem, we take into account the influence of adjacent plate on the plate under consideration. The general solution to this problem is obtained by superposing two elementary problems. The plate subject to symmetrically distributed moments and plate subject to anti-symmetrically distributed moment. The displacement of the plate is still expressed in summation of hyperbolic functions. And now we applied all the previous reason to our problem of tubular column subject to symmetrical point loads at each face. When only face 1 is loaded, the displacement of face 1 is obtained by combining of solution 2 in which the plate subject to 2-point load and solution 3a in which the plate is subject to symmetrically distributed moments. For the faces 2 and 4, only plates under symmetrical and anti-symmetrically distributed moment are considered. And for the phase 3, the place under symmetrically distributed moment is considered. All the constants are determined by using continuity condition at faces intersection. We have the same rotation and same bending moment. By the same way, the displacement of column faces is determined when only one other face is loaded. All the obtained results may be now represented by the matrix form. By inversing this equation, we obtain the relation between applied forces and the displacement of the column faces. The stiffness matrix is symmetrically only for a column of a square hollow section, but not for a rectangular hollow section. But when multiplying with this ratio, the modified stiffness matrix becomes symmetrical, and the matrix equation may be now represented by a model of springs as shown in the figure. The stiffness of spring are given here. To show the performance of the proposed model of the spring, we consider an example of a rectangular hollow section as indicated in the figure. Two sockets are implemented in phase 1 and 4. Forces are transmitted in the outward direction of phase 1 and inward direction of phase 4. Two methods can were carried out. The full element method with share element for each column face, and the proposed simplified element by modeling the behaviors as well as interaction between column walls by means of spring. The calculation results are given in the table. We can see that the maximum deviation between results obtained by two calculation methods is smaller than 5%. So calculation was made with the number of terms equal to 9, and the column length is equal to 5 times the section width. And when increasing the number of terms, smaller deviation between the two methods will of course be obtained. Now I finished my presentation with two conclusions. We proposed analytical solution for evaluating our planned displacement of tubular, rectangular, or square hollow section columns subject to two symmetrical concentrated forces, tension or compression at each column face. And we propose a model of spring taking into account the interaction between our planned displacement components of the column walls under tension and compression. This model of springs avoids a full 3D finite element modeling of the column walls, which is a rather complex and costly task in terms of the calculation times. Thank you for your attention.